So let's start to shift over to tree diagrams. So here we go. There are 7 black socks and 2 blue socks in a drawer. 2 socks are removed. What is the probability that the colors match? So let's read this again and try and visualize you have a sock drawer. There are 7 black socks and 2 black socks. Excuse me. There are 7 black socks and 2 blue socks in a drawer. 2 socks are removed. What is the probability that the colors match? So if we're going through this, if I have a big sock drawer and I've got 9 socks in there, 7 are black, 2 are blue, and I'm going to pick 2 of those out. Right? I'm just going to blindly pick them. I'm going to, rummage them around and just pick 2 out. I basically have 4 possibilities in terms of the color, right? We're just keeping track of colors here. I could get a black and black sock. I could go black and blue, then blue and black, or blue and blue. So those are my 4 options as we start to go through this problem, right? And since we're picking one sock and then picking another sock after that, this shapes out to be a tree diagram. So let's graph this tree diagram. I can feel the 4 branches. Okay. Right, so when I pick my first sock, again, this is just, we're keeping track of color, not size, shape, whether they're old or new, whether they've got holes in them, nothing like that. All we're keeping track of is this categorical variable of color. So I've got that I could pick a black sock or I could pick a blue sock. Now let's think about the probabilities associated with each of these branches, right? You've got, at this point, you picked no socks, so you've got 9 socks in the drawer. So my sample space is 9 socks. Of those 9 socks, 7 were black. So I have a 7 out of 9 chance of picking a black sock, because this is going to be a counting problem, all right? Counting and a tree diagram. So as we look at this, right, I've got to have complementary probability. So if 7 out of 9 socks are black, by default, 2 out of 9 socks are blue. And they also told us that 2 socks were blue, okay? So that's the likelihood when I pick that first sock. All right, now when I pick that first sock, I'm not going to replace it. I'm going to leave it out. So let me go ahead and draw the next set of branches. So again, we could pick a black or a blue sock. So let me write this. We've got black sock. This would have been blue sock. Okay. And so we're gonna figure out what these probabilities are. Okay. So as I think about this, if I picked a black sock out the first time, how many black socks are left, right? So I had a 7 out of 9 chance, but imagine, like I picked a black sock out, right? So think about what your sock drawer would look like. So if I had black, wow, how can I distinguish black and blue? So let me do BK for black and what would it be? BE for blue. So black, let me put 7 of these up here. 1, 2, 3, 4, 5, 6, 7, and then I had 2 blues, okay? So I want you to imagine, right? I had my 7 black socks and my 2 blue socks. And what we're saying is we picked a black sock, right? So that's out of the drawer. So think about how many socks do I have left at this point? I have 8 socks left. How many of those socks are black? 1, 2, 3, 4, 5, 6. Because there were 7 black socks, but if I'm along this branch, I picked one. So there's only 6 black socks left out of the 8 socks remaining. Okay. Now let me replay this. All right, so here was my original 9 socks. Okay, so let's go again through this, right? So I pick a black sock, right? I'm along this condition. So I'm gonna just kick out that one because it's easier to see if I just do it on the side. All right, now what's the likelihood that I pick a blue sock? You can see I still have 2 blue socks left because I did not pick the blue sock the first time out. So I have 2 out of 1, 2, 3, 4, 5, 6, 7, 8. So 2 out of 8. And take note, these are complementary probabilities, right? They add up to 1. Okay, so let's replay this, but now let's try it with the blue sock. So let me reset. Okay, so here we go. I picked a blue sock, right? So I'm gonna knock off this blue sock, okay? So then what's the likelihood I would have picked a black sock? Well, if I picked a blue sock the first time, all 7 of my black socks are still left. So I have a 7 out of 8 chance of picking a black sock. All right, now if I picked a blue sock, what's the likelihood I pick a blue sock again? Well, I only have that one blue sock left, so it's 1 out of 8. Okay. So again, thinking about this, the first time you pick a sock out of that drawer, there were 9, 7 were black, 2 were blue. The second time you pick a sock out, there's only 8 socks left. And it really depends on what you picked the first time out. If you picked a black sock, there's only 6 left, and there's still all of your blues left. If you picked a blue sock, there's all of your blacks left, and only 1 of your blues left. Okay? So there's the tree diagram. But now let's figure out this question. It says, what is the probabilities that the colors match? So basically, we got to figure out which branches do we want to include. So let's see, we've got top, 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 bottom, bottom, top, bottom, bottom. So here we go. Do the colors match if I go on the top, top? Black, black. Those colors do match, so I want to include that. I would like that branch, okay? Let's look at top, bottom. I go black, blue. Those are not matching sock colors, so I do not want that branch. Let's go bottom, top. Okay, again, blue, black, not matching sock colors. I do not want that branch. And then we got blue, blue. Those are matching. So let me go ahead and highlight that branch. All right, so I ultimately want 2 branches. Okay, and again, these are disjoint events. You can't pick 2 black socks and 2 blue socks at the same time. You're in one of those 2 categories. So I would like this branch and this branch in my answer. So let's do, I want the probability that colors match. All right, so that would say I want the probability of a black sock and a black sock and I'm going to run out of room, so I'm going to put it here, plus the probability of a blue sock and a blue sock. So whenever you have more than one branch you want to include, you want to just add those disjoint probabilities or add the separate branches. Now for black sock and black sock, I'm going to multiply those 2 numbers. So I'm going to have 7 over 9 times 6 over 8. I'm going to add to that blue and blue, and again I'm going to multiply these numbers, so I'm going to get 2 over 9 times 1 over 8. Right? So I multiply along the branches that I need, right? The respective branches. All right, so I get these products, multiply these two, but I add the disjoint branches. I add the separate branches. All right, so if I want to crunch this, I'm going to try and do it in my head today. So we got 42 out of 72. I'm going to add to that 2 out of 72. So if I'm looking at this, I've got my common denominators. I will keep my denominator. My numerator is 42 plus 2. I believe that is 44. I can't leave that answer right there as a fraction because it's not reduced, but I'm going to just find it as a decimal, and we're looking at about 61%. Okay. So if you've got some sock drawer with 7 black socks and 2 blue socks, there's about a 61% chance if you pick 2 socks out of there that they'll be the same color. All right. So with that one, let's move on, try number 6. I'm going to scooch this up. It's going to be another tree diagram, okay? So let me move this all the way to the top. And then we'll get going on this. All right, so you play tennis regularly with a friend, and from past experience, you believe that the outcome of each match is independent. For any given match, you have a probability of 0.7 of winning. The probability that you win at least one of the next 2 matches is blank. All right. So before we get going on this, let's just take a step back. So we're gonna play some tennis matches, and we're gonna play 2 of them. Okay? And they're saying the outcome of each match is independent, meaning whether I win or lose the first game has no bearing on whether I'll win or lose the next game. Okay, and I've got a 70% chance at winning. So that's pretty good. I tend to win a lot more often than I lose, right? 70% of the time I win, 30% I lose. What's the probability that I will win at least one of the next 2 matches? Okay, I think there's probably a good chance I'll win at least one of the next 2 matches, right? If I'm winning 70% of the time, it's not too terrible to think I could win 1 or 2 matches. So just looking at these options, I'm pretty sure I'm gonna rule out C, and I think I'm gonna rule out D also. Right, so just based on the fact that I win 70% of the time and they're talking about me winning, I do not think either of these is going to be the option. In all honesty, I don't think A would be the answer either, because 70% of the time I'm winning, so I have a pretty good shot at winning at least one of those 2 matches. So right out the gate, I'm suspicious that B is the answer. That's what I think is the answer, just looking at the possible answers listed in this multiple choice question. But this is a tree diagram, so let's make the tree and then find out, hey, was my intuition, was it really 91%? All right, so if I'm gonna play a game and we're keeping track of winning or losing, I've got 2 options to put on my tree diagram. So let's go win, lose. So I could win or lose, and it says I win 70% of the time. These have to be complementary events. All right, this is binary. I either win or I lose, so this has got to be 30%. Okay, great. So I need to play 2 matches though. So let me put another set of branches, right? Another win-lose. Oops, let me not fill this in. Let's talk about it first. Okay, so since winning, right, the outcome of each match is independent. So winning is independent, or losing for that matter is independent. It means that the second time out, I still have a 70-30 split on whether I'll win or lose. Okay. So you ultimately have 4 options, right? And think about this. If you're playing 2 games, you could win both of them. You could win and then lose. You could lose and then win, or you could lose and then lose. There are your 4 outcomes, right? So if I was just gonna write this here, this is win-win, this is win-lose, you could lose-win, or you could lose-lose. And I could multiply all of these products together, and all of those products should add up to 1, right? So 70 times 70 is a number, 70 times 30, 30 times 70, 30 times 30. And what I mean by that is if we looked at this is 70 times 70, so this is 0.49. This is 70 times 30, this is 0.21. This is 30 times 70, 0.21, and 30 times 30 is 0.09. And those 4 numbers should sum to 1. That's how every tree diagram should work, is that ultimately your outcome should sum to 1. Okay, but with all that, that's just side chat. Let's take a look. We got probability at least 1 match. All right, so probability at least, I should say win at least 1 match. Okay, and we've talked about at least. All right, that phrase at least is synonymous with the symbol greater than or equal to. So I want to win greater than or equal to 1 match. Let me give this some space. So that means I either want to win 1 match or 2 matches. Because if you're playing 2 matches, you can think about this. Like you could win both, you could win 1, or you could win 0. And if I want to keep track of when I win at least 1 match, that means I win 1 match or 2 matches. Those are the options I want to include in my probability. So let's think about this. If I win and then win, that's 2 matches. So I want to include this outcome. Okay. If I win and then I lose, right, that's one win. I want to include that in my options. If I lose and then I win, 1 win, I want to include that. But here we go. If I lose and then I lose, I have 0 wins. 0 is not at least 1. So I do not want to include that branch in my answer. So how I'm looking at this, if I want to win at least 1 match, I could win and win, or I could win and lose, or I could lose and win. All right, those are the 3 separate branches that I want to include, because these are the branches where I'm winning at least 1 match, okay? So if I look at this, the probability of winning and winning, we've said it, but it's 0.7 times 0.7, right? I'm going to multiply those respective branches. Winning and then losing is, right, we're going to go top bottom, so I'm going to go 70 times 30. All right, losing and then winning, I'm going to go 30 times 70. So when I look at this, this is 49% plus 21% plus 21%. And when I add those 3 numbers together, we've got 0.49 plus 0.21 plus 0.21, and we're looking at 91%. All right, so my guess wound up being correct, and you might be thinking, well, of course your guess was correct, you're the teacher, but I just want you to see, if you're winning 70% of the time, and you're playing 2 matches, you have a pretty good chance at winning at least 1 match. Now, personally, I like to do this a little different. You've heard me say all semester, I'm lazy. So I think about if I want to win at least 1 match. All right, so I go, well, if I want to, let me write the word win. The only thing I don't want to include in this is when I lose both matches, right? Or win 0 matches. So since I know all of these options have to total out to 1, I can use the complement rule. So I will take my starting probability of 1 and I will subtract out the 1 branch I don't want, lose and lose. So I will do 1 minus, and I'll go 0.3 times 0.3. All right, and 0.3 times 0.3 is the number 0.09. So when I do 1 minus 0.09, I still get 0.91. Yeah. And the reason I prefer this is because I'm only calculating 1 branch's product, right? I just have to do this one and subtract it out because I don't want that branch. So that's how I tend to do things. I like to think about, well, I needed 3 branches to do it this way and only 1 branch to do it this way. And I got better things to do with my day. So I like to do the more efficient one. Okay. All right. So we got a couple more tree diagrams coming up.